All right, here in chapter 2, we're going to look at the only non-parametric test that we're going to be looking at, called the chi-square test, and specifically we're doing the chi-square for goodness of fit. There are two chi-square tests in this chapter. One is a chi-square test for goodness of fit. The other is the chi-square test for independence. We're only going to cover the chi-square test for goodness of fit because I think it's important for you to take a look at the chi-square test, but I don't want to go over multiple chi-square tests. If you wanted to read up on it, you certainly could, but we're not going to do that. So we're going to be focusing on the chi-square test for goodness of fit. It's a non-parametric test, which means that we aren't going to compare it to a population. We are only concerned about the scores that are available to us in our sample. So let's go ahead and talk about an example real quick to frame this, and we'll go through this example and then a couple of others by the time we're done here. A basic example from the book is that researchers wonder if there is an equal distribution of gender representation on cereal boxes. The things that researchers wonder about. It's a worthwhile endeavor, but I'm wondering why the first person thought of it in the first place. If there were, then the amount of male and female characters would be 50-50. Let's stop there for a second. If there were equal representation of gender, and by the way, they mean sex here, and barely that. They've reduced gender to male and female, but that's okay. That's the example that we're working with. If there were an equal amount of male and female characters, we'd expect it to be 50-50. That means that half the boxes would have female characters and half the boxes would have male characters, or at least there would be an equal mix. However, they observed that they found that the distribution of all the characters on the cereal boxes that they looked at was 996 males and 390 females. Already you can see that that distribution is not what we would expect just based on the proportions of male and female that there are in the world. So there are more males represented than females, and we want to know if it is disproportionate. So the idea is there a significant difference in the observed proportions compared to what we would expect? So the observed proportions in this case was 996 to 390. We expect there to be a 50-50 mix just based on random chance because there are approximately half male and half female on the planet, so we would expect that representation to be true on cereal boxes if it followed the same trend. The key idea of the chi-square test for goodness of fit is to determine if the proportions of the expected frequency based on chance or prior research matches the observed frequency. Let's take a look at a pretty simple formula. This simple formula is going to tell us if we have an equal distribution or at least a non-significantly different proportion of people, in our case, genders, on cereal boxes, but we want to know in general if there is a significantly different proportion of observed and expected frequencies in a distribution. So let's take a look at what this looks like. And boy, this kind of looks familiar. We've seen this format a lot in this class. We want to know what the sum of some value minus another value squared divided by another value is. In this case, we want to know what the sum of the observed minus expected frequencies squared is divided by the expected frequency. It's fairly simple. Let's just think about this for a second. If we took the observed frequency and subtracted the expected frequency, and we did that for every group that there was, and we squared that, and then we add them all together and divided it by the expected frequency, then we would have our chi-square statistic. Let's put some math to it, and this is one of the rare situations where I think that the math will actually help us understand something here. Now, here's a table that just generally lays out what we're talking about here. We had 996 males represented on those cereal boxes. We had 390 females represented on the cereal boxes. If we expected there to be a 50-50 split, because that's what the representation is in the world, if we took this same amount of representation, the same amount of characters, and split them equally, we would expect there to be 693 males, 693 females. We want to know if what we observed is different than what we expect. And we do that by using this formula. So let's take a look at this. The first step is to take the observed minus expected frequencies. So we take the observed male frequency, which is 996, minus the expected frequency of 693. We then square it and divide it by the expected frequency. We do that same process for the other group, which is the female group. 390 females were observed. We expected 693. We square that figure, which again helps us to get rid of negative numbers, divide it by the expected frequency. We carry out the math, so we do some subtraction. So 996 minus 693 is 303, plus, divided by 693, plus 390 minus 693, which is negative 303, divided by 693, keeping going with the math, equals 91,809 divided by 693, plus 91,809 divided by 693, which equals 132.48 plus 132.48, which equals 264.96. That gives us our chi-square statistic. You might be thinking to yourself, okay, so what? Now we know what the chi-square statistic is. Well, the chi-square statistic, like every other statistic we've looked at with z-scores, t-scores, f-scores, the chi-square score, or the chi-square statistic, is the measure of standard deviations away from the mean our score is. So the differences that we observed altogether are so far out of whack that those differences occur 264.96 standard deviations above the mean. Okay, above what mean? Good question. 1. If these two numbers are exactly the same, our chi-square statistic will equal 1. So if we observed, for example, 693, and we expected 693, all of our math would equal 1, which would mean that we would have exactly the observed frequency that we expected. But because the observed frequency is so different than what we expected, our chi-square statistic is very extreme. Now, we even haven't talked about what the cutoff chi-square statistic is, or even what the comparison distribution looks like. But we can tell right away that this is a very significant result because we haven't seen any numbers with standard deviations this big. But we're going to go through just to double check that that is actually the case. So what does the chi-square statistic mean? Well, it's a measurement, again, of number of standard deviations from the mean. The cutoff chi-square, so the chi-square value that we will use as our cutoff value for 1 degree of freedom at the p is equal to 0.05 level is only 3.841. Okay, now here's something interesting. 1 degree of freedom, how did we get that? Well, the degrees of freedom is equal to the number of groups minus 1. You might also see that written as k minus 1. K is the statistical symbol for the group, so the number of groups. So you can say n subgroups minus 1 or k minus 1 is the same thing. In this example, there are only 2 groups, male and female. 2 groups minus 1 equals 1 group. That's 1 degree of freedom. So for 1 degree of freedom at the 0.05 significance level, the cutoff chi-square value is 3.841. Our chi-square value is 264.96. That is much farther away from the mean than our cutoff. And we're going to look at the distribution graphically to indicate that as well. It indicates a significant result, but what does it mean? Well, if we look at this, again, wonderful looking spaghetti graph of chi-square cutoffs, we recognize that for each degree of freedom, the curve looks different. And this follows the same kind of logic as the situation with our F distribution, where we have a lot of theoretical math that tells us what the cutoff is. And again, as a gamma distribution, I don't encourage that you look too much into it unless you really want to become a math major. Suffice it to say that someone's done an awful lot of work to help us out. So you can look at table, well, I guess it's 11.2 in this book, pardon me. That provides the cutoff chi-square values for the given degrees of freedom and p-values. That's actually this right here, but it's in a different place in your book. So the chi-square statistic is the number of standard deviations away from the mean that the particular score that we found was. So we will look at this, and we know that we had 1 degree of freedom, so our curve follows the red line. Our cutoff chi-square statistic from this test was 3.841, which is right about here. So if you look at the red curve, our cutoff is here, and our observed chi-square statistic is somewhere 2 feet off of the page. It's a long ways out there. Now, we didn't go through this using those hypothesis testing steps because we're setting up some of the concepts, but here we are already ready to get into the example because we've kind of covered everything we need to as far as understanding. Remember, the goal here is to determine if the distribution of scores is significantly different than what we would expect to see out of a distribution. Now, before we go on, I want to kind of just talk about something real quick. If we have no other information about a group that we are measuring, for example, let's say that we're breaking people into 3 different groups, and let's call them elementary school, middle school, and high schoolers. And we wanted to know how many people were in elementary school, how many people were in middle school, and how many people were in high school. We could just measure that, and we would assign them each to a group. Well, let's see. Person number 1 is in 3rd grade, so they're in elementary school. And we do that for, let's say, 900 people. If we didn't have any other information to go on, and I asked you, how many people do you expect to be elementary school students? How many do you expect to be middle school? How many do you expect to be high schoolers? You would just think to yourself, well, there are 3 groups, so my best guess is that 300 of them would be elementary school, 300 would be middle school, and 300 would be high school. Our best guess without any other information about what we expect to see is you take the amount of people that are in your sample and you divide it by the number of groups and just assume that the groups are equal sizes. And that's what we do in many cases where we don't have any expectation about what the actual sizes of the groups are. We just assume that they are equal. That's what we did for this example. We assumed that the expected frequency should be equal between the 2 groups. We're going to get into our other example and discuss another example of when we have a certain expectation. So we are using an example again about sex, but it tends to be something that's fairly concrete for us to be able to put some numbers to. So what we want to do is we need to determine the goodness of fit by finding the observed results and comparing them to the expected results, which are going to be based on chance. For the sake of the example, there are 12 female students and 6 male students. Is this a significantly different proportion of students compared to an expected equal distribution? And as always, we're going to test this at the p is less than 0.05 level. So in this example, we are going to be wondering if there is a different proportion than what we expect if the proportions were equal. We just expect, if we don't have any other information, that there would be an equal number of male and female students in the classroom. So we are going to figure this out. When we go on to step 1, we still need to identify the research question and identify the populations and the null and research hypothesis. So the research question is the proportion of male and female students significantly different than what we would expect if the proportion were 50-50, or if the groups were equal, whatever you wanted to say. Population 1 is going to be the distribution of students in class. Population 2 is going to be based on a distribution of students if the proportion is 50-50. So again, we're not creating necessarily a comparison distribution. It's more like a comparison curve. So the research hypothesis is that the proportion of students' sex in the class is significantly different than expected, or that the chi-square value will be greater than 1. Because remember, if the proportions are the same, that means that you're going to have a chi-square statistic of 1. So we want to know if our proportion is significantly different, greater than 1, which means that we're looking for a chi-square statistic greater than 1. The null hypothesis is that the proportion of the student sex in the class is not significantly different than expected, or the chi-square value is less than or equal to 1. And we know that that is a hypothesis statement. We really know that our chi-square statistic is going to be less than or equal to the cutoff. But in this step, we don't know it, so our best estimate is just 1. In step number 2, we're going to compare our results to a comparison distribution that's based on a chi-square curve with 1 degree of freedom. We have 2 groups that we're concerned about, male and female. That means we have 1 degree of freedom because n groups, or k minus 1, is equal to 1. 2 minus 1 is 1. In step 3, we will determine our cutoff chi-square statistic that will tell us when to reject or fail to reject the null hypothesis. The cutoff chi-square statistic for 1 degree of freedom at the 0.05 significance level is 3.841. So if we plot our cutoff, we can see that if we have a chi-square statistic, or if we have a proportion that is significantly greater than a proportion of 3.841, then we have a significant result. If not, then we don't. So we will fail to reject the null hypothesis if our statistic is less than or equal to our cutoff. If it's greater than our cutoff, then we will reject the null hypothesis. Moving on to step number 4, we do the math that helps us to figure out our chi-square statistic to find out what the proportion is for our result. So we have our table with female students and male students. We observed 12 female students and 6 male students. What we expect is a certain proportion of the total number of students. So if we look at it and we think that there are 2 groups, okay, 1, 2, and if there are 18 people altogether, we know logically that if we have no other information to go on, we will just assume that the groups are equal. And if that's the case, then we think that half of the number of people will be male, so 0.5 of the number of students will be male, or female, excuse me, and 0.5 of the male students, excuse me, half of the students will be male, 0.5 times n, so half of the number. If we plug this in, the number of students is 18 because 12 plus 6 is 18. Half of 18 equals 9, and we expect the same number for male students if we expect equal proportions, so 0.5 of n, or 0.5 of 18, is equal to 9. So we calculated our expected number of students in each group by multiplying the total number by half. When we do the math, we find that 12 female students minus, which is our observed number of female students, minus the expected of 9 squared divided by 9, plus the number of male students minus that we observed, minus the number of male students that we expected squared divided by the number of male students, or excuse me, it is a number of male students that we expect of 9, which is equal to 3 squared over 9 plus negative 3 squared over 9, which is equal to 9 over 9 plus 9 over 9, which is equal to 1 plus 1, which is equal to 2. Our chi-square statistic is 2. I guess I'll speak to this just for a moment. I don't want to kind of give away the answer. But our chi-square statistic is 2, meaning that we have a proportion of 2 to 1, or there are twice as many female students as male students. That proportion is not significantly greater than our rejection, our cutoff score, which indicates our rejection zone. So we're going to go to step number 5 and look at it in terms of our null hypothesis. Our null hypothesis is that chi-square is less than or equal to 1, and we know that that 1 is really just a substitute number for our cutoff, so we actually plug in our cutoff. So our chi-square statistic, which was 2, is less than or equal to the cutoff score, which was 3.841. We ask ourselves the question about the null hypothesis. Is 2 less than or equal to 3.841? It is, so that means that this statement appears to be supported, so we fail to reject it. So we fail to reject the null hypothesis, which suggests that the proportion of male to female is not significantly different than what we would expect. When we create a result statement, we do it by indicating a few things that are consistent with how we have been doing result statements. So we talk about the purpose of the test, the statistical outcome, and then the result sentence. So the result statement looks like this. A chi-squared test for goodness of fit was conducted to determine if there was a significant difference between the expected distribution of sex and the observed distribution of sex in the class. There was a non-significant difference in the proportion of sex. The chi-square statistic was 1 degree of freedom was equal to 2, with a p-value of 0.157, which I pulled from SPSS, and you could too. These results indicate that there was not a significant difference in the distribution of male and female students in the class, and there was a failure to reject the null hypothesis. It's a very simple statement. In this example, we're going to take a look at a situation where we don't expect that the groups are equal, but that we expect them to have a certain proportion based on an estimate of what we would expect in a first-year introductory class. So here's the example. We want to know if the proportion of class standing of students in an introductory class fits the expected proportions of students who would typically take the class. We need to determine the goodness of fit by finding the observed results and then comparing them to the expected results based on what we would expect in an introductory class. For the sake of the example, there are 50 students in the class. You expect that the class would be 60% freshmen, 20% sophomores, 10% juniors, and 10% seniors. We'll see what the actual proportion is in step 4, but we're going to test this at the 0.05 level. In step 1, we look at the research question. Is the proportion of class standing of the students significantly different than what we would expect if there were if the proportion were 60, 20, 10, 10, meaning 60% freshmen, 20% sophomores, 10% juniors, 10% seniors? Population 1 is the distribution of students in the class. Population 2 is the distribution of students if the proportion is 60, 20, 10, 10. That's our comparison distribution based on the chi-square. The research hypothesis is that the proportion of class standing, let me rephrase that. There we go, that makes a little bit more sense. The proportion of class standing in the class is significantly different than expected, chi-square greater than 1. And again, we know that it's not going to be 1 as our cutoff, but that's our best estimate of the tipping point without any other information about the distribution. The proportion of class standing is not significantly different than expected. Chi-square is less than or equal to 1. That's our null hypothesis. Let's go to step 2 and take a look at what our comparison distribution looks like. In this example, we're using another chi-square curve, but this time it's based on 3 degrees of freedom. And we talked about how the chi-square distribution changes shape based on degrees of freedom. And if you look at this, the chi-square distribution for 3 degrees of freedom is kind of this blue curve here that I approximated on this slide. So this is our chi-square distribution. And if we have an increase in our cutoff, whatever that is, we'll find that out in step number 4. Step number 3, whatever our cutoff is, if there's an increase in our chi-square statistic that we observed in the distribution of the class, then we will consider it to be significant. But this is the curve that we're looking for, and somewhere on here we will find our cutoff chi-square value that equals 5%, because we're working with the 0.05 level. Let's go ahead and look through that in step number 3. Step number 3, we're going to use a chi-square distribution to determine the cutoff chi-square. We will reject or fail to reject the sample's chi-square value. We're going to use that alpha level again of 0.05, or the cutoff value equal to 0.05 with, that should be 3 degrees of freedom, not 1, because we have 4 groups. 4 minus 1 equals 3. So with our chi-square distribution, we have 3 degrees of freedom at the 0.05 significance level. That's 7.815. So that is the chi-square statistic that we are working with. For a chi-square statistic of 7.815, our result would be significant if it is greater or in the 5% tail, or we would fail to reject it. It would not be significant if it's equal to our cutoff or in the other 95%. And again, this is a chi-square distribution based on 3 degrees of freedom. In step number 4, we're going to do some calculations. So for now, we're going to set up our table that helps us to identify the observed versus expected frequencies. So in this particular case, in order to find the observed and expected frequencies, we refer to the example, which gives us our observed frequencies. And we just plotted these here. We observed 20 freshmen, 16 sophomores, 2 juniors, and 12 seniors. Now, when we calculate the expected frequencies, we use that same proportion that we talked about earlier. So it is 60% freshmen, 20% sophomores, 10% juniors, 10% seniors. There we go, all better. So that's what we expect our numbers to be. Now, when we figure this out, what if we have some expected values, we need to find the number of people in the sample, which we found to be 50, both from the example and by adding up our observed frequencies. So what we do is we multiply the number of people in the sample times the percentage of time we expect them to occur. So if there are 50 people in the sample, we multiply it by 0.6, which is the same as 60%, we get 30. We did the same thing for sophomores, juniors, and seniors, so our expected frequencies become 30, 10, 5, 5. Our new table indicates that we observed 20 freshmen, we expected 30. We had 16 sophomores, we expected 10. We had 2 juniors, expected 5, and 12 seniors and expected 5. We want to know if what we observed is different than what we expect based on the distribution that we felt was reasonable for an introductory class. We can do that using the same formula as before. We'll just have a little bit more work to do because we're using 4 groups instead of 2, but it's the same arithmetic. So in this case, we have freshmen, sophomores, juniors, and seniors. We took the expected number of, the observed number of freshmen minus the expected number. We squared it and divided it by 30. We did the same thing for sophomores. We observed 16, expected 10. We square that and divide it by 10. Same thing for juniors. Observed 2 minus the expected of 5 squared divided by 5, which is the expected. And then last for seniors. We observed 12. We expected 5. 12 minus 5 squared divided by 5. Going down to the next line, we do a little bit of the math. So 20 minus 30 is negative 10 squared over 30, plus 16 minus 10, which is 6 squared over 10. 2 minus 5 is negative 3 squared over, that should be outside the parentheses. I'm not going to worry about it though. Negative 3 squared over 5, and then 7 squared over 5. Going down to the next line, we did our math. So negative 100 squared is 100 over 30, 36 over 10, 9 over 5, 49 over 5, and then I divided those out. 3.33 plus 3.6 plus 1.8 plus 9.8 equals 18.53. Our proportion is 18.53. What this means is that we have a combined amount of proportion difference of 18.53. We know that our cutoff was in the neighborhood of 7.5, and our chi-square statistic equals 18.53. Let's take a look and see what that means in the next step. If we plot it on our chart, it's kind of way out here, so it's a long ways away. So our chi-square statistic needs to be less than or equal to 1 in order to support the null hypothesis. And we know that it's not actually 1. Now that we actually have the cutoff, we plug it in. So our chi-square statistic was 18.53, less than or equal to 7.815. If this statement is true, then we can fail to reject the null hypothesis. If this statement is false, then we reject the null hypothesis. 18.53 is not less than or equal to 815, which means that we reject the null hypothesis. This indicates that the proportion of, it is a proportion, but the proportion of the distribution of our students in that class is significantly greater than a proportion that we would expect based on our expected values of 60, 20, 10, and 10. Let's take a look and see what the conclusive statement would look like on this. A chi-square test for goodness of fit was conducted to determine if there was a significant difference between the expected distribution of class standing and the observed distribution of class standing in a class. There was a significant difference in the proportion of class standing. The chi-square statistic of 3 degrees of freedom is equal to 18.53 with a p-value of less than 0.001. It's so low that we don't even state what it is exactly. We just state that it's less than 0.001. These results indicate that there was a significant difference in the distribution of class standing and therefore a rejection of a null hypothesis. That's it. So for the chi-square for goodness of fit, what we are trying to do is determine if the result that we got is significantly different than what we would expect in terms of the proportion of individuals in a study. This could be really important for representation, by the way. Think of something like ethnicity. and you expected there to be 50% Hispanic people, 20% Asians, 10% white, and 20% black. If you expected those proportions and you got something very different than that, you might think that there is some misrepresentation going on. So it's an important thing for social scientists. What's more is that it's also something that you can use to test to see if you have equal enough groups to do any other particular test. So let's say that you wanted to do an ANOVA, but you wanted the groups to be relatively equal. What you would do first is you would do a chi-square for goodness of fit to find out if the groups are adequately similar in order to do your ANOVA. There are other ways that we use the chi-square test. Many of them have to do with what we call assumptions of parametric and non-parametric tests. So we have to be careful of how we consider the importance of chi-square, even though it's kind of at the end of the chapter, or excuse me, the end of the course, and it appears to be not incredibly helpful for inferential statistics. It's still very important in determining if our statistics can be run in an adequate way and for representation in our sample. So if you have any questions, let me know. If not, I look forward to seeing what you can do with the data analysis.